Hello there, I'm Tanuj 24BEC0539 and I'll be giving my presentation on the second module, that is electromagnetic waves. So in this module we'll be covering various topics. First of all, we'll start with the basics of vector calculus. We'll be discussing about the curl, gradient, divergence. After which we'll be following it up with line, surface, and volume integrals, and then we'll discuss about the Stokes and Gauss's theorems. After that, we'll discuss about the Maxwell's equations. We'll discuss about the physical significance and the anomalies in them, and what modifications were made to these equations. After that, we'll be transforming these equations from the integral to their differential forms, and we'll be also deriving these equations in free space. We'll also discuss about the general solution for EM wave equation. We'll also talk about the transverse, transverse nature of these waves, and in the end, we'll be discussing about Hertz's experiment to prove the existence of EM waves. So, without further ado, let us begin. So first of all, let us start with the del operator. The del operator is a vector differential operator that acts on scalar and vector fields. And in 3 dimensions over here, we can see that the del operator can be written as dou by dou x of I cap, dou by dou I of j cap, and dou by dou z of k cap. Now the del operator can be applied in different ways depending on the type of field. As for the example of gradients, when it is applied to a scalar field, the result is a vector field that points in the direction of the steepest increase. In the case of divergence, when it is applied as a dot product with a vector field, it measures how much the field spreads out or converges. And when it is applied as a cross product to a vector field, it measures the field's rotation. Now let us discuss about the divergence of a vector field. Let us consider some vector f. Now its divergence can be mathematically represented by this equation right here. This equation represents the del term, which we have seen before, the partial differential term, and this is the vectors term in its components. When we perform a dot product between these two, we get this equation right here, which is a scalar term, which basically shows us that the divergence of a vector is a scalar. Now let's look at these two figures. Here we see um, the field lines converging outwards, basically diverging. And in this figure right here, we can see that the field lines are converging inwards. So this case over here is when the divergence of the vector is positive, and this case over here is when the divergence of the vector is negative. When the divergence is positive, we can call it a source, and when the divergence is negative, we can call it a sink. Next, we can move on to the curl of a vector. The curl basically measures the rotation or twisting of a vector field. So, for example, for a vector f, the curl of f is the cross product between the del operator and f. And here is the mathematical representation of the cross product. A key point to be noted is that the curl of a vector is also a vector, and that the direction of a curl is always perpendicular to the plane of the circulation. We'll be seeing this in the next slide. Over here, as we can visualize that the curl of the vector, here we can see the circulation is perpendicular to the plane of rotation, to the plane of the circulation. So before we jump into the second derivative, let us understand what is the gradient. So gradient is applied to scalar fields like temperature or pressure or anything like that. The gradient points in a direction where the field increases most rapidly, and its magnitude basically tells you how steep the increase is. So with that, we can begin with the second derivative. From basic calculus, we know that the second derivative is used to measure the rate of change, and second derivatives can be generalized through the Laplacian operator over here. So the Laplacian operator is crucial in understanding some very important properties of gradient and divergence and curl. So the first important property that we have over here is that the curl of a gradient is always 0. Now the second important property over here, similarly to the curl of a gradient, the divergence of a curl is also always a 0. As you can see over here, the divergence of some curl of some vector v is 0 using this property over here. The third important property is that the curl of a curl can be expressed as the gradient of the divergence minus the Laplacian of its vector. Now that we know these three important properties of Now that we know of these three important properties, let us start with integration. In integration, we will cover line, surface, and volume integrals. First of all, line integrals. A line integral sums up a field along a curve. For some, let's say, some scalar field f, it calculated calculates the accumulated value along its path. And over here, we can see the line integral for a closed path. Now, surface integrals. A surface integral sums up a field across a surface. So, for some scalar field, it calculates the total flux over its surface. So, for some vector f, the surface integral here calculates the total flux generated by the surface. Basically, the perpendicular arrow you see over here, this is the flux coming outward from the surface. Now the surface integral over some closed path. Over here we can see over a closed path, as you can visualize from these figures down here, over a closed path, the surface integral can be calculated this way. Next we have the volume integral. The volume integral sums up a scalar or a vector field over a 3D region for some scalar field, let's say f over here. So in open regions, these integrals describe localized properties of fields, and in closed spaces, they relate to fundamental theorems like the Stokes and Gauss's theorem that we will be studying right now. Now let's talk about some theorems of vector calculus, that is the Gauss's divergence theorem and Stokes theorem. These theorems connect integrals over different dimensions and make our calculations simpler. So, the Gauss's divergence theorem. This theorem relates the flux of a vector field through a closed surface to the divergence field inside the vector. So, it basically states that the total outward flux of some vector f through a closed surface S is equal to the volume integral of the divergence of f over volume V enclosed by some surface S. What this means is that the total outflow of the field through the surface equals to the spread of the field within the volume. So now the Stokes theorem. The Stokes theorem relates the circulation of a vector field around a closed loop to the curl of a field over the surface bounded by the loop. So what it basically states is that the surface integral of the curl of a vector function over a surface bounded by a closed surface is equal to the line integral of the particular vector function around that surface. This tells us that the total rotation of the field around the loop equals to the twisting of the field over the surface. So in simpler terms, the Gauss's theorem converts a surface integral into a volume integral using divergence, and the Stokes theorem converts a line integral into a surface integral using a curl. Both these theorems are quite important to calculus and bridge the gap between properties like divergence and curl and global properties like basically flux and circulation. So this will be the end of our vector calculus segment, and now we can start with the Maxwell equations, and one by one we will go through all of the Maxwell equations, and we will also discuss the anomalies and their physical significances and their properties in free space and all that. So let us begin with Gauss's law. So the Gauss's law relates the electric flux through a closed surface to the charge enclosed within that surface, and here we can see the mathematical expression that describes the Gauss's law, where E stands for the electric field, the A stands for the surface, the Gaussian surface, which is this is the Gaussian surface, and then Q stands for the charge enclosed by the surface, and epsilon naught is the permittivity of free space. So the Gauss's law tells us that the total electric flux that flows out of a surface is directly proportional to the charge inside the surface, which means that if there's no charge inside the surface, the total electric flux is zero, and if there is a charge inside, the flux depends only on the amount of charge and not on the surface, not on the shape of the surface or where the charge is located inside the surface. So for example, if we were to place this charge inside a sphere, regardless of its position, the flux through the sphere would be equal at any position of the charge, as long as it encloses the charge, the surface encloses the charge. Now let's discuss about the Gauss's law of magnetism. So the Gauss's law of magnetism states that the net magnetic flux through any closed surface is always zero, and it can be mathematically expressed as this, where B stands for the magnetic field, dA stands for the closed surface. So what this equation tells us is that unlike electric fields, magnetic fields always form closed loops as there are no magnetic monopoles. This law helps us understand that magnetic monopoles do not exist. So we can understand this better with the help of an example. For example, if we closed a magnet inside some surface, the net flux going outwards will be equal to the net flux coming inwards of the surface. So basically the key difference between both of Gauss's law, the Gauss's law for electric fields and the Gauss's law for magnetism, is that in Gauss's electric law, the flux depends on the charge enclosed, but for magnetic fields, since there are no magnetic charges, the net flux is always zero. Now let's move on to Faraday's law. So Faraday's law is crucial for understanding how magnetic fields can produce electric fields. Faraday's laws state that a changing magnetic flux through a surface induces an electromotive force in a loop surrounding that surface. So Faraday's law can be mathematically expressed as this equation over here, where E stands for the electric field, dl is the path along which the electric field is occurring, and phi is the net magnetic flux. As for why do we put this minus sign before this equation, is due to the Lenz's law, as it states that which means the EMF induced. As for why do we use this negative sign before this equation, the negative sign comes from the Lenz's law, which means the induced EMF opposes the change in flux that it creates. What this means is that if the magnetic field through a loop changes either in strength or direction or area exposed to the field, an electric current is generated for the loop. So Faraday's law is quite important in understanding the working principle behind generators. For example, when you rotate a coil in a magnetic field, the flux changes continuously, producing an alternating current. So in summary, the Faraday's law explains how electricity and magnetism are interconnected, forming the basis of electromagnetic induction, and how it is the foundation for technologies like transformers, electric motors, and generators. Now we will discuss about the Ampere's law, another fundamental law of electromagnetism that describes how magnetic fields are generated by electric currents and changing electric fields. So Ampere's law states that the magnetic field in space around an electric current is proportional to the electric current which serves as its source. So Ampere's law can be mathematically expressed in this way, where B stands for the magnetic field, dl is the small surface, and mu naught is the permeability of free space, and I is the current enclosed by the loop. So Ampere's law tells us that a steady electric current generates a magnetic field around it, forming closed loop. For example, a current carrying wire creates concentric magnetic field lines around it, and that changing electric fields can also produce magnetic fields even without a physical current. This explains how electromagnetic waves propagate, with electric and magnetic fields continuously creating each other. So now let's talk about how Maxwell's equations, which are typically written in the integral form over here, and how we can convert them into their differential forms by taking the help of Gauss's divergence theorem and Stokes' theorem. We will go through all these equations one by one and solve them. So here's Gauss's law in its integral form, as we've seen before. And now we will use Gauss's divergence theorem. So the LHS can be written as this. So see how we've converted the surface integral into a surface integral over a closed surface into a volume integral using Gauss's divergence theorem. So now we have two equations, equation number 1 and equation number 2. So when we substitute the second equation in the first equation, we get this new equation. Now we will integrate the right hand side and take the constant, the permittivity of free space outside, and replace the enclosed charge with the charge density across some volume V. Solving this, we get the Gauss's law in its differential form. Now for the Gauss's law of magnetism. Here is the Gauss's law of magnetism in its integral form, as we've seen before. Similarly, how we solved the Gauss's law of electric fields, we can also use the Gauss's divergence theorem here, and we can write the LHS in this form. And again, we've expressed the closed surface integral into a volume integral, and we've made two equations, equation number 1, equation number 2. As we substitute the second equation in the first one, we get the integration of divergence of the magnetic field vector over magnetic field vector with respect to V is the volume, is equal to 0. So basically the divergence of the magnetic field is 0, and this is the differential form of Gauss's law of magnetism. Next we'll move on to Faraday's law. So here's Faraday's law in its integral form, as we've seen before. Here, instead of using Gauss's divergence theorem, we will be using Stokes' theorem. As you know that Stokes' theorem can convert the line integral over some closed path into a surface integral. So here we have converted the electric field over some closed path L to the curl of the electric field over some surface S. Now we have two equations over here. As we substitute the second equation into the first one, we get, so now we have this equation over here. As we integrate the right hand side with respect to some surface S, we bring out the constant of time, the partial derivative, and we integrate b dot ds with respect to some surface. Now as we solve this equation, we get that the curl of an electric field is equal to the negative change in magnetic field over some time. And we finally got the Faraday's law in its differential form over here. Next we will be converting Ampere's law from its integral form to its differential form, also using the Stokes theorem over here. Now we will convert the left hand side, which is a line integral, that is the magnetic field over some path, over some small path L, to the curl of the magnetic field over some surface S. Here again we have two equations, equation number 1 and equation number 2. We will be substituting the second equation into the first one, and we get that the surface integral of the curl of the magnetic field is equal to mu naught into the current enclosed by it. Now we will be integrating the right hand side with respect to some surface S, and we will be bringing out the constant, the mu naught here, the constant of permeability of free space will be brought out. And here we have replaced the current enclosed by J, which stands for the current density, and we'll be integrating this with respect to some surface S. Solving this, we get that the curl of some magnetic field B is equal to mu naught J, where J stands for the current density, and this is the differential form of Ampere's law. Now that we've done converting all of Maxwell equations from their integral forms into their differential forms, let us break down the significance of each of these equations and understand what they reveal about electric and magnetic fields. So for Gauss's law, we have understood that a positive charge creates field lines radiating outwards, while a negative charge creates lines pointing inward. And this law basically connects the electric field to the charge distribution in space, giving a local and point by point description of how charges influence an electric field. So In summary, basically it tells us that charges create electric fields. As for Gauss's law of magnetism, we have understood that from this law that magnetic poles, monopoles cease to exist, and that magnetic fields are generated by moving charges or changing electric fields, but they do not have isolated sources themselves like electric fields do. So magnetic fields are continuous and looped. Next, the Faraday's law of electromagnetic induction. So we've understood that electromagnetic induction, which is the basis of many electric devices like generators and transformers and inductors, and how they work, how that a time varying magnetic flux can produce an electric field, and why there is a negative sign from the Lenz's law as it indicates the induced electric field, which opposes the change in magnetic flux, maintaining the conservation in energy. And as for Ampere's law, we have understood that a magnetic field is produced due to conduction current density. So here a magnetic field can be produced by uh, a magnetic field is produced due to the conduction current density. So the gist of this is that currents and changing electric fields can generate magnetic fields. So these four equations are quite important as they help us unify electricity with magnetism, and we can understand from here how electricity and magnetism influence each other and interact each other, and thus we can easily predict the nature of electromagnetic waves like light, and as electromagnetic waves are basically a combination of oscillating electric and magnetic field. Next, let us discuss about the anomaly in Ampere's law and how Maxwell resolved it with a critical modification. So, as we've seen before, initially this is what the Ampere's law states. Now, the law we see here, this worked well for steady currents, but a problem emerged when in cases involving time varying fields. So I'll just tell you how like this anomaly was discovered by Maxwell, and how what modifications he made to resolve this anomaly. So let's consider a charging capacitor over here. So a current flows through the wire to the capacitor plates, creating a magnetic field around it. However, between the plates there is no physical current. Instead, there is a changing electric field as the charge on the plate builds up. Now, if we would have used Ampere's law to describe this, the magnetic field around a loop between the capacitor plates would have been incorrectly described as zero, as the current enclosed by these plates is zero. However, that is not the case, as we can see that a magnetic field clearly exists, therefore, there is a flow of current through these plates. So, this gap in Ampere's law meant it couldn't account for situations where current seemed to disappear, such as in the cases for capacitors. So, to resolve this inconsistency, Maxwell introduced the concept of displacement current. As we can see here, this is the term for displacement current, which is mu naught epsilon naught multiplied by dou t of the electric flux. So Maxwell modified Ampere's law to include this additional term. So Maxwell said that not only current produces a magnetic field, but a changing electric field in vacuum or free space also produces a magnetic field. So the initial term for Maxwell's law, this one, had been modified by Maxwell to make this term, and now this law is called Ampere's Maxwell's law, where we can see both the terms for conduction current and displacement current. So as you can see here, now these are the corrected form of all the Maxwell equations, even though the initial three are still there as they were successful in describing the natures. However, this fourth equation was anomalous and had to be modified by Maxwell. So the modified term suggests a magnetic field is produced due to conduction current density and varying electric field. So now, why was this modification important? It was important because it completed the symmetry between electric and magnetic fields, just as how magnetic fields induce electric fields, as we've seen from Faraday's law over here, as you can see it over here. And now we can also say that changing electric fields can produce magnetic fields. Now we will be talking about the Maxwell equations in free space, where there are no charges or currents. This represents the simplest form of these equations, focusing on the intrinsic relationship between electric and magnetic fields. So as you can see here, the rho, which stands for the charge density, equals to 0, and the current density also equals to 0, as we are in free space. Now as we substitute these values into their respective equations, we get new equations from their general form to these equations in free space. So from here we get that in free space the divergence of an electric field is 0, the divergence of a magnetic field is also 0, the curl of an electric field is equal to the negative change in the magnetic field with respect to time, and the curl of a magnetic field is equal to the displacement current. So what insight we get from these equations when we express them in free space is that Maxwell's equations predict that electric and magnetic fields can sustain each other and propagate as waves. The solution to these equations can describe electromagnetic waves such as light, which is the speed at which all electromagnetic waves travel at. So now we'll be deriving the electromagnetic wave equation in free space. As you know, there's no charge or current density in free space, so we'll be considering rho and j, both of them is 0. We've written down all four of Maxwell equations in free space over here, and let's start with Faraday's equation, and let's operate a curl on the third equation, that is the Faraday's equation. Now we know that the curl of a curl can be expressed in this form, as we've learned earlier. We get this new equation, and we can substitute the curl of the magnetic field with the displacement current term from Ampere Maxwell's law. We've replaced the divergence of the electric field as 0, as we know that in free space the divergence of the electric field is 0, as from the first Maxwell equation in free space. So after that we can simplify this equation to look something like this. Similarly, we can perform the curl operation on the fourth Maxwell equation using the same property of the same vector property as the curl of a vector. Here we can express this term, this LHS term, as this, and as we solve for the curl of this displacement current term, we can simplify this as to become this term over here, and we can replace the curl of the electric field with the negative change in magnetic field over some time from the Faraday's law, and simplify this equation to this term right here. Now in both terms over here we've replaced 1 by under root mu naught epsilon naught by c which stands for the speed of light, and substituted c into both of these equations right here. So we know that in a wave equation this term squared stands for the velocity of the wave. So when we substitute the values of epsilon naught and mu naught into the value of c, we get 2.99776 into 10 to the power 8 meter per second. So this basically concludes that all EM waves travel at the speed of light in free space. Now we will convert both of these equations into their general solution. So we will find out the general solution of the EM wave equation. Now for both of these equations, let us consider x to be the direction of the propagation of these waves. So in that case we can expand this Laplacian and replace it with dou square upon dou x square for both of these terms. So we get dou square E upon dou x square and dou square B upon dou x square, where E and B stand for electric field and magnetic field respectively. So from here we get these equations over here. So these equations are the general solutions to EM waves, where Emax and Bmax are the amplitudes of these waves. K is the wave propagation constant, which is 2 pi by lambda. Omega is the angular frequency, and phi is the phase constant. So the general solution shows that electromagnetic waves are basically oscillating electric and magnetic waves um, that propagate together, and that both electric and magnetic fields dynamically create each other as they move through free space. With this, we'll try to understand wavefronts and plane waves. So wavefronts are parallel surfaces connecting equivalent points on adjacent waves. So as we can visualize here, that these points, or here's an easier visualization of a spherical wavefront. So basically from some origin point, these waves are propagating outwards. And here's another type of wavefront. Here's a cylindrical wavefront where also the wavefronts are propagating outwards, and here's a plane wavefront where the waves are propagating outwards from some surface. So a plane wave is defined as a wave whose value remains constant, that is, whose wavefronts are parallel planes throughout a plane, as we saw in the last slide over here. Here are plane wavefronts. So here are some properties of a plane wave. A plane wave's wavefront are equally spaced, and the EM plane, the electromagnetic plane wavefronts propagate at the speed of light, and plane waves can be represented by the solution of wave equation, which is the solution that we just derived a few slides back over here. So plane waves are idealized representations of electromagnetic waves with uniform fields over infinite planes. The concept of wave fronts helps us basically visualize how these waves propagate and understand the symmetry in field of space. So a plane EM wave is a wave in which the E and B fields have same magnitude in a plane which is perpendicular to the direction of propagation. The plane wave's magnitude, phase and orientation depends only on the variables associated with the direction of propagation. Now let's have a look at the solution of the EM wave in one direction and understand its transverse nature. So in one dimension, the solution to the electromagnetic wave describes how electric and magnetic fields propagate along a single axis. So here we'll consider the direction of propagation to be the x-axis. So as we know that the general solution for these equations are sinusoidal in nature, and both E naught and B naught, the amplitudes of the electric field and magnetic field, are constant vectors, but their phase term only varies along the z direction. So here we use the Maxwell equation in free space to prove that the electric field and the magnetic field are perpendicular to each other while they travel through free space. So basically, if the electric field oscillates in the y direction, the magnetic field will oscillate in the z direction, and vice versa, and therefore are mutually orthogonal to each other. So this reveals one of the key characteristics of EM waves, that is that they are transverse in nature, and both electric and magnetic field move perpendicular to each other. So now we'll move on to our final segment of where we will discuss about Hertz's experiment, which was a pivotal demonstration in proving the existence of EM waves, which was predicted by Maxwell. So let us begin by first understanding the apparatus in front of us. So first of all, we have the transmitter part of the apparatus right here. This includes the battery, the induction coil, the capacitor plates, the metal rod, and the spark balls. So the battery supplies energy and the induction coil generates a high voltage current. And the capacitor plates store charges and release it in sudden bursts. Now the high voltage generated across both of these spark balls, S1 and S2, helps create rapid oscillations of charge, generating electromagnetic waves. Now, this is the receiving part of the apparatus. The receiving loop is a circular loop of wire with a small air gap over here, and this air gap is the micrometer air gap. And in this, the receiver detects the EM waves by producing small sparks by using these spark balls over here. So basically, the transmitter radiates these electromagnetic waves, which travel through through space and induce a current in the receiving loop. So the procedure that went through this experiment is that, so first of all we have to generate the wave. So Hertz closed the switch to allow the battery to energize the induction coil. This caused a high voltage discharge across the spark gap in S1 and S2, producing oscillating currents in the transmitter. These oscillations then created electromagnetic waves which propagated outwards from the transmitter. Now, the receiving loop is placed near the transmitter. When the electromagnetic waves reach the loop, they induce a current, resulting in a tiny spark across the micrometer air gap. And the sparks in the receiver confirm the presence of the electromagnetic waves. So the observations that Hertz made from this experiment was that he noticed that the sparks in the receiver appeared only when the transmitter and receiver were aligned properly. He also observed the phenomena like reflection, refraction, and interference, proving the wave-like nature of EM wave. So here is an real life apparatus, setup of the apparatus that was created by Hertz. So, Hertz's experiment conclusively demonstrated that electromagnetic waves exist and propagate through space. He also showed that these waves travel at the speed of light and exhibit all the properties of waves, such as interference and reflection and all that. This experiment was crucial for development of many other technologies that we see further on in the future and which we still use today. So yes, this experiment was quite pivotal and in the field of science. And yes, and with this we'll be ending our presentation. And this is Tanuj here, 24BEC0539, and I'll be signing off. Thank you very much, and have a nice day.